Hey guys, welcome back. We are on Vodcast Chapter 16, Sections 5 and 6. Make sure you have your guided notes ready, and I would recommend that you also keep a calculator with you, okay? Here we go. This should be a review of the information that was presented in these two sections. I'm going to go through the review pretty quick so that we can look at our sample questions, which are a lot more important than the content here. So I'm going to go pretty quick here. So starting in Chapter 16, Section 5, it's all about strengths of acids. It says acids are often divided into categories such as strong and weak. It says one measure of the strength of an acid is its acid dissociation equilibrium constant, or K sub A. So the K sub A is just like the equilibrium constants that we've been working on so far. And I give you an example here in this box. You have an acid, general formula HA. And when it enters into water, it will ionize the water into hydronium. And then you'll get the negative ion that was left over from the negative part of the acid. So the general formula here would be just like an equilibrium. You always put products over reactants. So it's a concentration of the ions you produced over the acid, and it's very, very simple. So what does K sub A tell you? Well, when it's really, really large, when the value of K sub A is really large, that means you have more products than you have reactants, which is good. That means that it fully ionized. But when K sub A is really small, that means you're going to have a weak acid. So I gave you a couple examples. Hydrochloric acid, K sub A is about 1,000. And then compare that to acetic acid, which we know to be a weak acid. Acetic acid's K sub A value is 1.8 times 10 to the negative fifth. Now, that's a weak acid. Here is a very, very, very small number. It says when it is very small, we have an extremely weak acid, almost negligible. So compare that to, like, say, the value of water. K sub A for the value of water, usually about 1.8 times 10 to the negative 16th. So very, very, very small. And remember, we usually like to compare pretty much everything to water. So here we go. It says, did you know, just in case you forgot this, the P in pH and POH is an operator that indicates the negative of the logarithm, and we've talked about that before. So, of course, there's going to be something called pKa. pKa is the negative of the logarithm of the acid dissociation equilibrium constant. So, general formula here for pKa is negative log K sub A. So, and you guys already know that pH is equal to negative log concentration H. So now you've got this pKa. So you've got pH, POH, pKa, right? And it says, but be very careful when you're calculating these pKa's because it sometimes can be confusing. It says the only disadvantage of using pKa as a measure of the relative strength of your acids is the fact that large numbers now describe weak acids. And of course, small numbers now describe strong acids. So you have to be very, very careful if you're looking at pKa versus K sub A. So these are the same acids that we compared on the other screen. You've got hydrochloric acid is now negative 3. Acetic acid is now 4.7. And then check out water, 15.7. So you need to be very, very careful. Make sure you know the difference between Ka and pKa. Alright, this brings us back to the discussion of conjugate acid-base pairs. It says, just as the magnitude of Ka is a measure of the strength of an acid, the value of Kb, what do you think Kb really means? I mean, come on, right? If K sub A is the acid dissociation constant, well then K sub B would be the base dissociation constant. So it says the value of Kb reflects the strength of conjugate bases. So it says, consider what happens when we multiply the Ka expression for generic acid HA by the Kb expression for its conjugate base. So remember, A negative, this would be the conjugate base of this acid when it ionizes. So we get the following equation. Ka times Kb is equal to the acid, or is equal to the equilibrium expression for water. You guys remember water, the self-ionization of water. So remember, we compare everything to water, right? Ka times Kb will give you 1 times 10 to the negative 14th. By the way, that's the auto-ionization of water. So pKa plus pKb, by the way, will give you a very famous number, 14. So it all kind of wraps around itself and is all kind of the same concept, but we're just throwing in equilibriums because we want you to realize that acids and bases in pretty much every reaction in chemistry really is an equilibrium. Sometimes you finish all the way to completion, and so you'll have a very strong K value, a very high K value, and sometimes you won't. And therefore the K value will be very low. Alright, so here is a quick table. This can be found in your book too. It says, because the product of Ka times Kb is a relatively small number, 1 times 10 to the negative 14th, either the acid or its conjugate base can be strong. But if one is strong, that means that the other one must be weak. So it's kind of like a ratio or a proportion. When one is strong, the other is weak. It says, thus, a strong acid must have a weak conjugate base. So this brings us back to that table that we were trying to explain to you in class. It would have been so much easier if I could just explain Ka and Kb. Remember how like they have one table in your textbook on page, if you have your book, on page 676 on the bottom? That's a really nice one, but the one that I was looking at, that's not it. This one, on page 672. On page 672, there's a nice table right there, and it was comparing the strength of the acid to its conjugate base. And it would have been very nice if I could have just taught you K sub A and K sub B. So remember that if you have a strong acid, you can have a weak conjugate base, and vice versa. Alright, so let's jump into some examples. This first example is in your book. Here we go. You've got HCN. Do you remember the name of that? Hydrocyanic acid. And it's ionizing in to make an H+, which means that it's acting like an acid. So K equilibrium would look like the products over the reactants, and this is what you need to realize is really just your K sub A value. Since it's acting like an acid, we can call it the Ka instead of just K equilibrium. So this is from page 628. I don't know if that's right. I think this is a previous version. Sorry guys, this is a previous version of your text. So I used this different version of the text a while back, and it looks like I forgot to change it over. Let me see if I can find it in your textbook. Yeah, it doesn't look like I can find it in your text. Oh, here it is right there. This is on the bottom of page 685. Page 685. Okay, so here we go. Here's your practice problem. What is the pH of a 0.3 molar HCN solution? So we have the value of Ka, and we have the molarity of the HCN solution beginning, like the beginning. Take a wild guess as to what you're going to have to do. You've got a K value, and they gave you the initial concentration. You're going to have to set up an ice box. Okay, because whenever they give you a K sub A value, especially a K sub A value that's really, really small, that means that this is a pretty weak acid, like you can tell by the K sub A value. So here's our ice box. We need to do our initial concentrations that we know of, which is just the HCN. We do not know the initial concentrations of the H or the CN ion, but let's see if we can fill in some of the information in between. We have a K sub A value. The K sub A value will help you to figure out your equilibrium expression. You need to stoichiometrically figure out like the X value. Remember, X is the change. So you know you're going to lose one portion of your HCN, and you will make one portion each of your products. So if you do your equilibrium expressions, this is what you'll have. Now remember, K sub A is at equilibrium. So you have your K sub A value. You need to plug in your equilibrium expressions like this. Let's see, here's your ice table again. Remember, this is what your K sub A is equal to, right? So now you just plug in the products. Here's your product. Those were both x's, so this is x squared divided by 0.3 minus x. And this is your K sub A value. So we're going to solve for that x value. It says since the value of x is going to be very small compared to 0.3, we can assume that 0.3 minus x is about 0.3. Because if you actually do solve for x, you'll realize that with this k sub a value, it is so teeny tiny compared to your 0.3. In other words, I'm telling you that the x value is almost negligible. It says if x is more than 5% of the initial value, so your initial value is 0.3. If it's about 0.5, that initial value, then you probably have to do a quadratic equation. So that saves an awful lot of time. If you look at your k sub a value and you solve for x and it ends up being really small compared to your initial value, if it's more than 5%, you really should do your quadratic. But it's less than 5%, man, it's negligible. So you really got lucky in this particular instance. This is really easy to solve for. So really k sub a is x squared over 0.3. Very nice. Makes it all nice and tidy. So now you just solve for the x. Sorry, that's not very legible. Let me see if I can fix that real quick. Oh, computer. It won't let me do it. Anyway, you should have got, oh, hold on. Anyway, you should have got an x value right here. Let me change that to a different color. 1.21 times 10 to the negative fifth. Alright, so there's your x value, right? We still want to figure out the pH, and the pH is all about that H+. So if that right there is the concentration of your H value, you just plug it in to the formula for pH. pH is equal to negative log that, and you should get a pH of about 4.9. So remember, we made a pretty huge assumption. We assumed that the x value itself was going to be really small compared to 0.3. And if you look at your x value right here, we were absolutely correct. That is way small. In other words, 0.3 minus that number would be about 0.3 still. So just realize that sometimes your x value is very tiny. And so luckily you usually don't have to worry about it for weak acids. Weak acids, look at that k sub a value. It's super small. Okay, so let's keep going here. Oops. Let's see how it looks now. Oh yeah, that's much better. Okay. So, another topic that was covered is something called percent ionization. It says percent ionization is another method to assess the strength of an acid. And it's very easy. It's basically the higher the percent, the stronger the acid. And it says percent ionization of a weak acid decreases as the molarity of the solution increases. So here's an interesting graph for you to figure this one out. It says again, percent ionization of a weak acid decreases as the molarity of the solution would increase. So a weak acid just basically becomes weaker and weaker as you increase the concentration, because you've got more water, less of the acid being able to ionize with it. So, general formula here for the percent ionization. So whatever the percent is, that is equal to the equilibrium concentration of your hydrogen ion divided by your initial concentration of your acid. So remember, H+ ion on top, acid initial concentration on the bottom, and then multiply it by 100. So here's a good practice problem. It says, what is the percent ionization of HCN from the previous problem? It says percent ionization would be equal to this molarity. This is the molarity at equilibrium, right? The H+ at equilibrium. Divided by the initial concentration of the acid, which was 0.3. And then you times it by 100. So look at that percent ionization, 0.00403. Pretty low, isn't it? Just wanted to show you that example. Okay, I'm going to show you some more examples on a different PowerPoint here. Right here. Okay, so basically this is the same example that you saw on my PowerPoint. Hold on, actually, we're going to go down a little bit. See. Here we go. Let's do this guy. This is sample exercise 16.13. You'll find this on page 687. I know, I'm sick. I probably shouldn't be doing podcasts when I'm sick, but what are you going to do? Okay, so this particular section, 16.6, is a fairly long one because there's a lot of example problems. And so I just wanted to kind of make sure that we were all doing the same example problems. So here we go. It says, calculate the percent of HF molecules ionized in a 0.1 molar HF solution, and then again in a 0.01 molar HF solution. So we have two different concentrations. You have one that is 0.1 and the other one that is 0.01. So remember, it's very easy to do these. All you have to do is figure out the equilibrium concentration of your H plus ion, okay? That means you're going to have to do an ice table. So, it says we're asked to calculate the percent ionization of two HF solutions of different concentration. From Appendix D, or something that they give you in a problem, you will have to look up its K sub A value. So, they looked up the K sub A value for HF, and they found it to be 6.8 times 10 to the negative 4. That's a pretty weak acid, so we're probably going to have to do an ice table. It says we approach this problem as we would in the previous equilibrium problems. You must begin by doing your ice tables. So the first concentration that they're starting with is that 0.1 molar. You know you're going to lose one part of this, and you will make one part of each of these. So here's your equilibrium expression here. You're going to have the x squared on top. You're going to have that 0.1 minus the x on the bottom. By the way, most acids, we'll talk about this later, will have an x squared expression on the top of their K sub A. Alright, so again, you've got this minus x thing going on. So, it says, when we try solving this equation using the approximation that the 0.1 minus x is equal to 0.1, in other words, the x is negligible, you're going to attain an x value that is 8.2 times 10 to the negative 3 molar. The question is that negligible? Your initial concentration was 0.10. Your change would be 8.2 times 10 to the negative 3. The question is that negligible or not? In other words, remember the rule, it was about 5%, right? So this is what I want you to do. Take that 8.2 times 10 to the negative third, divide it by 0.1, times it by 100, and I want you to see what percent you get. So let's see what we get. We get 8.2 e negative 3 divided by 0.1, and then make sure you times it by 100. I get about 8.2%. Dun, dun, dun. So it says because this value is greater than 5% of the 0.1 molar, we should work the problem without an approximation. In other words, you're going to have to use it doing a quadratic of formula. So remember that check. If it's 5% or lower, it's negligible. But in this particular instance, it is not. So as you can see, they started doing a quadratic of formula. They got x squared on one side, they've got this, they've got the expression of K sub A. They reduced it to this formula right here. So since there's no number in front of the x squared, this is your A. This means that A is equal to 1. B would be this number right here. C would be negative 6.8 times 10 to the negative 5. So you got to be very careful about how you plug in your positives and your negatives into this formula. So negative B, so we're going to plug that in, plus or minus b squared. Luckily b is a positive integer, so we got a positive number in there. Minus 4, there's your 4. A, C. Now A is positive, C is negative. And you see how there's usually a minus sign right here? Look, they changed it into a positive sign. Okay, so make sure that you're watching your positives and negatives. I think that that's the most critical part of this particular guy, so it does become kind of difficult. Alright, it says this quadratic can be solved using the standard quadratic formula. Substituting the appropriate number gives x is equal to 7.9 times 10 to the negative 3. Remember, you usually get two solutions for x, so remember that one of them is probably a lot larger than that. And remember, your initial concentration on this guy was 0.1. There's no such thing as negative concentration, So I'm sure that the other value was probably higher than 0.1. So this is probably the only solution that makes sense. Alright, so then it says percent ionization. All you need to do, you know that this is X, your value of X, which is also equal to your concentration of H+. So all you have to do is put this concentration on top, put the 0.1 molar on the bottom, times it by 100, you get about 7.9%. Now part B is going to be pretty much exactly the same ice table, right? Except for one important difference, your initial concentration. But the X value should still be the same. It's the same acid. So your X value is going to be a little bit different just because of this guy, your initial concentration. So make sure that you resolve for this particular guy. And so they got an X value of 2.3 times 10 to the negative third. And by the way, notice this time that the 0.010 minus X is negligible, because I guarantee that your X value would be less than 5% of the initial concentration. So they probably just threw out this whole part right there. Oops, sorry. They probably just threw out that minus X. So they probably just divided it by 0.010. So slightly different value of their X. Plug that into the formula right here. Times it by 100. And you get 23% is ionized. Okay, let's keep going. Okay. Alright, I think we don't talk about polyprotic acids yet. No, we do not. Okay, so those are the two examples that I wanted to show you. Pretty short podcast. I'm sure you guys won't not mind, though. Alright, you guys, I'll catch you next time. Sorry I sound so terrible. I'll see you later.
Hey everyone, welcome to Chapter 16, Sections 7 through 11. Make sure you have your guided notes with you before you do this, and also make sure that your outline is already done. Alright, let's begin. At the beginning of Section 7, they start talking about basic solutions. So for an example, I thought we'd just pull this one up. What is the pH of a 0.15 molar solution of ammonia? So the thing that you need to know about ammonia is that when it's in contact with water, that's where we're going to make our OH ions in the product side. So ammonia and water is necessary to combine to make your OH ions. So notice our Kb expression here. Products on the top, reactants on the bottom. You could look up your Kb value. You would need to, because ammonia is a weak base. So look up that Kb value. Here it is. And we can use this expression to try to figure out what goes where. You'd probably want to think either about doing potentially an ice table, or maybe you can think this through for yourself. The initial concentration of the ammonia is 0.15, so you've got your denominator. But your numerators, these ions, these are the ones that are in question, so these would both be X's. Here's an ice table to kind of further explain it a little bit. So these are your products right here, and this is your reactant. You will consume a little bit of your reactant, which technically we should probably put in a minus X there, but I hope you understand how to and when to eliminate that minus X. Alright, there's that 5% rule. What you could simply do is use your Kb value that was given to you on the previous slide, which was, 1.8 times 10 to the negative 5. 1.8 times 10 to the negative 5. And then you could just do a real quick check, x squared over 0.15. Then you would have to make sure that the X value is less than 5% of this particular initial value. So here's our final expression. We decided that we can ignore the minus X from the 0.15. So we're going to go through and try to solve for our X value. The thing that you need to know is what that X value means. Those are your two products. All right. One of your ions was OH. The other ion was the NH4+. But this is the one that really we need to concentrate on, because that's your OH ion, and that's going to lead you to your pH. So now we know that our OH ion concentration is 1.6 times 10 to the negative third molar. You're going to have to do the function for pH so that you can go negative log of that concentration. But do remember that concentration OH will lead you to POH. So you need to make sure that you follow through with one more step. Subtract it from 14. Now you have your pH, and this makes sense. All right, ammonia is basic, so we'd expect that pH to be greater than 7. Now let's look at sample exercise 16.16, using pH to determine the concentration of a salt. So what you need to realize is that certain salts, certain ionic compounds, have bases or conjugate bases that we really need to pay close attention to. So what you have here is sodium hypochlorite. The salt has a sodium ion in it, and then you have hypochlorite on the backside. We don't care about the sodium ion, but we should recognize that this particular ion, when it is in the presence of water, is going to undergo an interesting reaction where this guy obviously is going to gain a hydrogen from water. Now if it gains one of these hydrogens, you're going to make some OH ions. And then you'll come back over to this particular acid, which is, a weak acid. We don't really have to worry about it. But we do need to worry about the OH ion. Alright, so the plan of attack. We should probably figure out what that Kb value, and in this problem they do reference equation 16.37, which is in your textbook on page 692. The reason why it's important to grab that is because we need the Kb value right here. Alright. So the bottom line of this problem is we're going to figure out how much solid sodium hypochlorite we need to add to a 2-liter solution to make that pH go up to 10.5. So what we start with is calculating the initial concentrations, which we don't know. We don't know how much salt we need to add to the solution. So this time for your initial, look at this ice table, you have an unknown initial concentration of your ClO. But since they gave us the pH that we are supposed to be using, or that we want to get to, we can go through and figure out the OH ion concentration necessary to get that pH. So that's the work that you see here. We are going to, remember, you have to be careful since they're giving you pH, but this equation gives you OH ions. You need to be careful, go from pH to POH, so that we can get to our concentration OH. Okay, so the very first step here, I'm going to take 14, subtract the 10.5. That'll give us the POH. So then to figure out the concentration of the hydroxide ion, just go 10 to the negative 3.5. And this right here represents the concentration of OH that is necessary to get to a pH of 10.50. So we're going to plug this into our ice table. We know that we need this much of the OH ion being produced. So you see those values dropped here. But remember, you have two products, so we need that also dropped here. Okay, we have an unknown initial concentration. We are going to be making 3.2 times 10 to the negative 4 of each of these ions in the product side. So remember, you're going to be consuming a little bit of this initial concentration of the reactant. And so we finally get our ice expression for the equilibrium down on the bottom. Alright, you have a Kb value. So our Kb value, again, from the equation 16.37 on page 692, they gave us our Kb. You have this expression on the top, which is your products. You have this expression on the bottom, which was your reactants. Doing some simple algebra, you can extract that x on the denominator, and you should come up with 0.13 molar. This would be the concentration of this particular ion that we would initially need at the beginning of the solution. So one final thing to remember, don't forget that the volume of the solution is 2 liters. This is molarity, this is volume. So how many moles of sodium hypochlorite would be needed? Remember, molarity is moles per liter, so 0.13 molar times 2.00 liters will tell you exactly how many moles of NaClO you need to add. You should get 0.62 moles. Now, if you wanted to, you could convert this to mass if they asked you. For reinforcement, you should try that practice exercise where they give you a solution of ammonia in water has a pH of 11.17. What is the molarity of the solution? So go ahead, you're obviously going to need some Kb values in this particular one. Now on to section 8, the relationship between Ka and Kb. Ka and B are related in this way. This is the formula. When you multiply Ka and Kb, you should get Kw, which is 1.0 times 10 to the negative 14th. So one of the things you should notice about this particular diagram is the fact that we've got some different types of acids, and then we also have their conjugate bases listed. So I thought I'd just draw your attention to a couple interesting facts. So over here we have HF. When you look at this value for the Ka, you'll notice that it is times 10 to the negative 4. But then when you come over here and you look at its conjugate base, you'll see that this is times 10 to the 11. So looking at the magnitude of these two, HF would make a much better acid than this guy would make as a base. This is carbonic acid, and then this is the conjugate base for carbonic acid. Look at this value. This is times 10 to the negative 7th. This is times 10 to the negative 8th. So technically, this one makes a little bit of a better acid than this guy makes of a base. And then if you were to multiply the Ka and the Kb together, you should get the Kw value, 1 times 10 to the negative 14th. So come down and look at this last one down here. The OH ion is like almost 100% wholeheartedly a base, so it would be really silly to think of this as being an acid. Hydroxide ions, it's almost impossible to rip off that last hydrogen ion. And so when you come over here, look at this guy. So oxide ions in water, very hard to find. They will react with the water around them. Therefore, if you know one of them, you can always go through and calculate the other one. Acid-base properties of salt solutions. This would be section 9. Nearly all salts are strong electrolytes because they can fully dissolve in water. Therefore, salts in solution exist entirely of ions. Acid-base properties of salts are a consequence of the reaction of their ions in solution. So the ions typically react with water, known as hydrolysis. Many of the salt ions can form OH or H plus ions when they react with water, and this process is called hydrolysis. Here's an example. This is the weak conjugate base formed from acetic acid. This conjugate base will react with water, and in the process of doing so will produce OH ions. Anions from weak acids are basic, just like the above example. So what about anions from strong acids? Well, chloride ions came from hydrochloric acid. Well, you need to remember that strong acids produce conjugate bases that are not going to react with the water solution around them. So this situation really only exists when you're working with weak acids or weak bases. Anions with ionizable protons are what we call amphoteric. They can react as an acid or a base, but this is very rare. So here is a conjugate base from a polyprotic acid. So this probably came, you can see the negative 2 charge, this probably came from H3PO4, and this one right here probably came from H2CO3. So with these particular guys, there are tricks, and usually it has to involve the use of the Kb and the Ka values of these conjugate bases to figure out what they have to do. All cations, except for those of alkaline metals or heavier alkaline earth metals, are weak acids. So we'll talk about why certain metals do react with the water that they are placed in. The pH of a solution may be qualitatively predicted using the following guidelines. Salts derived from strong acid and strong bases are neutral. So if you have two strong solutions, acid-base, they will make a neutral solution. Here's another example. You've got some calcium hydroxide, strong base, and you have some nitric acid, strong acid. Calcium nitrate here is not going to react with the water in it, so it does produce a neutral reaction. So let's look at the second situation when you have a strong base and a weak acid. Anytime you have a strong base and a weak acid in an ionic compound, we consider those solutions basic. So let's take a look at some examples. The Na in sodium hypochlorite probably came from a strong base, NaOH. This ion, however, came from a weak acid, HClO. So whenever you are combining this kind of salt where you have a strong base and then you also over here have a weak acid, the solution will be basic. And the reason why is because this conjugate base from the weak acid is not strong. And so what it's going to do is it's going to cling to the water. So you look at a hypochlorite ion associating with water, and in the process of doing so, it'll produce OH ions and that weak acid, HClO. So look, on the product side, you have OH ions. The other example that you have here is barium. This probably came from barium hydroxide, so BaOH2. And then you've got acetate. Now we should know that acetate is the conjugate base of a weak acid, acetic acid. So it's pretty easy on this one to figure out which one is stronger, which one is weaker. So this is our little problem child right here. And so when you stick this weak conjugate base in water, it's going to do the process of so when you stick this weak acid in water, it will undergo hydrolysis. And so this ion right here is going to pop one of the hydrogens off, and so you're going to get that OH ion again, and then you're going to get your weak acid back, C2H3O2. Because this weak acid doesn't want to ionize, it doesn't want to push to the left. Right? This guy right here, it can't push to the left because it's weak. So this reaction is predominantly pushing from the left to the right, which makes that OH ion. The third sample that we have here is whenever you have a salt that is derived from a weak base and a strong acid, that is going to make it acidic. So let's see if we can find some examples of that happening here. So in the front right here, NH4, this came from a weak base, ammonia, NH3. And this guy right here probably came from a strong acid, HCl. So really the problem child in this situation is the NH4 ion. So the NH4 ion is going to undergo some hydrolysis. The NH4, when in the presence of water, is going to give up its extra hydrogen ion. So you're going to get H3O ions, and the other product is going to be your ammonia. Okay? Remember, the ammonia is weak, so it's not able to push the reaction this way. All right? Because it's weak. Therefore, the reaction is going to be predominated to the right. And that's where you have your acid ion. So it kind of makes sense that these solutions will become acidic. So in this other example, the magnesium, Mg, is going to make this particular compound. Now you're going to have to think about your solubility rules on this, because magnesium hydroxide is not fully soluble in water. Therefore, this is a weak base. The other guy over here, the nitrate, came from a strong acid, HNO3. So really the problem child here is your magnesium ion. So the fact that the magnesium hydroxide here is partially insoluble kind of makes for a sticky situation. Technically what you have is a weak base ion combined with a strong acid from the nitrate. So really, this is the problem child in this particular situation. What is happening in solutions that make these salts acidic or basic? Let's look at that barium acetate as an example. The barium acetate dissolves into ions, the barium and the acetate ions. Okay, it says these ions will attempt to react with water. That's called hydrolysis. So let's take a look at the barium ion first. When the barium ion is in the presence of water, because of that positive 2 charge, it's going to take those hydroxides off of the water, and therefore you're going to make 2 hydrogen ions. Since barium hydroxide is a strong base, okay, this guy right here is a strong base, the equilibrium lies almost entirely to the left. So really, hydrolysis is not going to happen. No H plus ions are going to form because this guy is going to push the reaction this way. So these don't happen. Let's look at the other side of the problem. Your acetate ions. Now your acetate ions, when it is in the presence of the water, because of its negative sign, it's going to rip off the hydrogens from the water. You will be producing your OH ion. So since this guy right here, your other product, is a weak acid, it's not able to ionize, it's not able to pop that hydrogen back off. So this way, not very dominant. Therefore, the equilibrium is going to push to the right side. And so you're going to make hydroxide ions, and that makes that solution slightly basic. What about a salt that has a weak acid ion, weak base ion? So these are some of the examples from previous. The ion with the largest ionization constant will have the greatest influence. So what I did is I tried to combine this ion, you've seen it before, it's the ammonium ion. The ammonium ion, when it's in the presence of water, is going to pop off that hydrogen ion in the front to make your ammonia and H3O, your acid. But then you also have the gosh darn F ion, the fluoride ion. When it's in the presence of water, it's going to make that HF and your leftover, right? OH. So which one dominates? Let's take a look at a practice problem. Will a solution of NH4F be acidic or basic? Which one wins? So like I said, you're going to have to look at the Ka and the Kb values for both of these and compare them. So which one is dominating? Is it the NH4 ion who's making an acid? Look at the Ka. Or is it the F ion who's making OH ion? Look at the Kb. Since the Ka is slightly larger than the Kb, technically the solution should be slightly acidic. So there are some salts that contain ionizable protons, which make it kind of a sticky situation. The pH of these salts is affected not only by the hydrolysis of the anion, but also by its Ka value. Consider this, an acid with the formula HX. For this substance to be an acid, we need the following to happen. The HX bond must be polar. Occasionally, you might have the X being a metal, and so the bond polarity would flip. If that were to happen, the substance would be a base. So there is one example, but this is very rare, like I said, HNA, or as we usually write it, NaH, because it's basic. The second thing that has to happen is that the HX bond must be kind of weak enough to be broken, and this has to do with like electronegativity. So the greater the difference in electronegativity, usually that has a determining factor about whether or not the bond is easy enough to be broken. And then finally, the conjugate base has to be stable. So the more stable the anion, the more acidic it's going to become, because it's able to ionize. So let's check out some of the strength of binary acids here. So this is just like the previous screen where you have just H and X. So we're just kind of going through the periodic table and looking at just binary acids. So do you remember back in honors chemistry when you were learning about predicting the charge of ions, when you got to carbon and silicon, there was a bit of a problem, because carbon can lose 4 electrons or gain 4 electrons to have an octet. And it's no coincidence that these both have no acid or base properties. Number one, the bond is not polar, okay, so these are purely covalent bonds. And number two, the bonds themselves are fairly easy to break, yes, but they're not going to have a conjugate base that is stable. So could you imagine like CH3, -1 charge? Not very stable at all. The next situation that you have is you have nitrogen and phosphorus. Notice they're in the same group, and they also both are weak bases. So in this particular case, yes, you've got some bond polarity, which is nice, that's helpful, and they both have a hybridized bond, which we'll talk about much later in the year, that supports the hydrogen being ripped off of the water. So you know how ammonia can rip off the hydrogen of water when it's in the presence of water. It rips off a hydrogen, and that produces an OH, which that's the exact same thing that will happen with the phosphorus. But then once you breach over this side, you start getting to the opposite, where now you've got like a barrier between your bases and your acids. Notice water doesn't count, so oxygen's out. But over here you have a weak acid, this is H2S, and you start encroaching on where you've got some bonds that are going to be made that are polar, and that their electronegativity supports a bond breakage. In other words, their conjugate base is stable enough for there to be an ion present. So HF is weak acid, this guy right here. because the bond is so highly polar that the bond is has a high energy when you break it. So therefore HF doesn't dissociate much. So you can't make very much hydrogen ions out of HF. Compare that with HCl. Now the electronegativity difference between C and H is so small that the CH bond is nonpolar, so these guys right here, and so CH4 is neither an acid or a base. This guy right here, you should probably know that fluorine is one of the most electronegative atoms on the periodic table. Chlorine is a little bit less. So this breaking right here is very difficult to do. You have to have a lot of energy to do it. But this one right here, not so much energy required, therefore you make a better acid out of hydrochloric acid. Strength of oxyacids. Oxyacids contain OH bonds, and all oxyacids have some kind of general structure on the back. That Y is really what makes the oxyacid strong or weak. So it says the strength of the acid depends only on Y and the atoms that are attached to Y, what Y represents. So if Y is a metal, that means that it has a low electronegativity. In other words, it's willing to give away its electrons, which is nice. That's what metals do, they lose electrons. Well, if that happens, then the substance becomes a base. So here's an example of NaOH. You get this kind of nice breaking because this guy's willing to give that electron over to OH. So if Y is an intermediate electronegativity, kind of in the middle, the electrons between Y and O and the substance is a weak oxy acid. So it's all about the electronegativity value. So if you look at these examples down here, let's look at chlorine versus iodine. Chlorine has an electronegativity value of 3.0. And iodine has an electronegativity value of 2.5. So this guy has a stronger pull for electrons. So when you pull the electrons through to the carbon, that basically is going to expose this hydrogen ion. In other words, the hydrogen ion electron cloud, it's almost like the hydrogen becomes naked and exposed because all of its electrons are being pulled away. So over here, this one is less so, and so look at their H or Ka values. This one is to the power of -8. This one is to the power of -11. This is a much weaker oxyacid than this one, simply due to the electronegativity values of what it's attached to the OH. Okay, as the number of oxygen atoms attached to the Y increases, so you can make more than one OH bond, that's going to make the polarity increase. So consequently, the electrons on the OH bond are pulled away from the H, and this makes it even easier to ionize. So the strength of the acid will therefore increase. So here's some examples. We have this one right here where we have one OH. Check this guy right here. He's got an oxygen here, and then he's got an oxygen over there. This is really extreme. You've got 3, and then finally my favorite, you have 4 over here. Check this out. Increasing acidity over here. The more you can pull the electrons away from the atom in the middle, the stronger the acidity will become. So carboxylic acids, why can acetic acid ionize, but this one right here, it cannot? Well, you're going to have to look at the fact that you've got additional oxygen atoms on the carboxyl group, which increases the polarity of the OH bond and stabilizes its conjugate base. So the conjugate base of this exhibits resonance, further increasing the stability of the conjugate base. It's able to flip this electron around between these oxygens, which helps it. Here is an idea of what the resonance looks like. So this double bond can flip and move down here, and the negative value flips and moves back up. The carboxylic acid strength also increases as the number of electronegative groups in the acid decreases. So an example, acetic acid is much weaker than trichloroacetic acid. And here's their formulas. So on this one right here, you've got some chlorine sticking on the carbon at the end instead of hydrogen. So it says that the carboxylic acid strength also increases as the number of electronegative groups on the acid increases. So compare the electronegativity of hydrogen to that of chlorine. Chlorine is much more electronegative than hydrogen, so it's able to pull more of the electrons away, therefore making the acid a little bit more acidic. Hydrolysis of metal atoms. So metal atoms are positively charged and attract water molecules. All right, anything with a charge is going to attract water molecules because water is polar. And it's more specifically the lone pair of electrons on the oxygen atom. So the higher the charge on the metal ion, okay, and the smaller the metal ion is, you will get a stronger OH interaction. So both factors increase your acidic potential. So here's the summary. The smaller the ion is of the metal, so the smaller the metal, think about size of atoms and your trends on the periodic table. Atoms get smaller as you move from the left to the right, and they get bigger from top to bottom. So if you really want to talk about a small ion, you should be probably looking a metal ion. You should probably be looking at lithium. Okay, it's really small. But when you go down to the bottom of that group, so when you talk about like cesium and francium, those atoms are way bigger. The higher the charge, so +1 versus +2. All right, the +2 is going to have much more attraction for the water than a +1. So here's a practice problem. Number 1. Calcium ion versus zinc ion. Which one is more acidic in water? Well, they both have the same charge. So it's going to come down to size. All right, calcium is in the 4th period of the periodic table, and so is zinc. So you need to think about your periodic trends. What happens to the size of the ion when you go from the left side to the right side? Okay, size generally decreases. All right, so zinc is smaller, and therefore the zinc ion in the presence of water will be more acidic. Here's another example. Let's compare the calcium to the aluminum. First off, straight off the bat, the +3 ion stands out versus a +2. Okay, so aluminum is got that +3, which is going to interact more with the water. So therefore, it will be much more acidic than the calcium ion. Here is a visual representation of what I just said. So a +3 ion versus a +1. All right, and notice the size does kind of matter. You have a weak electrostatic interaction, and so you see this small pole here. But then over here you have this dramatic pole because this guy right here has a +3 charge. So the larger the charge, the more interaction you're going to get. The weak acid is on the left, the stronger acid is on the right.